Here you go. So today we're talking about removable discontinuities. There are different types of discontinuities. Today we're talking about removable discontinuities. All right. So all right. Here we go. Look at these two graphs. We have x plus 1 on the left, and on the right we have x squared minus 1 over x minus 1. What do you guys notice about these graphs?
One of them is discontinuous because it doesn't have discontinuous.
Good observation. So I heard two good answers. One is they're pretty much the same, and the other answer is, but one of them has a discontinuity, right? So these lines are exactly the same except for one little part, right? Now, what is f of 1?
2.
What is the limit as x approaches 1?
2.
What is f of 1 over here?
Undefined.
What is the limit as x approaches 1 over here?
2.
The limit exists, okay? When you have, so here's the thing. When you have a hole as a discontinuity, the limit still exists, right? And you'll notice that this limit is exactly the same as this limit. Okay? Now here's the problem though. Since this is undefined at 1, if you tried to use direct substitution, you would have a problem, right? If you tried to just plug that right in, you'd end up with an issue, right? Okay. But the limit still exists. Now I want to share with you guys something here. So fact number 1 is when a function has a hole, the limit still exists, right?
Yes, sir.
Now, fact number 2 is this. Here's the reason these two lines look almost exactly the same. If I were to factor the top, what would that be? And what do you notice there? And they're identical, right? So that's why they're the same. This is kind of like the reduced version of this. But unlike this one over here, this one does not have a hole because but this one does. And this one has the hole because it really does have that denominator which ruins it, right? So, but here's the thing. If I were to factor this and rewrite it like this, and then I tried to find the limit, can I use direct substitution now? And what would I get? The answer. What I did there was I removed the factor that was causing it to be discontinuous. So we call that a removable discontinuity. Okay? Now, that's fact number 2. So fact number 1 is a hole has a limit. Fact number 2, functions that have holes have removable discontinuities. Okay? So that's what I want you guys to grasp from that. So this was a little algebra trick, right? There's 3 different algebra tricks I'm going to teach you that will help you remove discontinuities. Okay? This is one of them. One of them is factoring. There's 2 other ones, and we'll learn those ones tomorrow. Okay? But that's what a removable discontinuity is. So a removable discontinuity is a discontinuity that can be removed by doing some kind of algebra where you end up basically with the same exact equation, but it's written in such a way that that discontinuity is gone now. And you can still find the limit by direct substitution. In fact number 2, that looks like a hole in the graph then when that happens. Something I probably should have put in here that I didn't is, so if this is a removable discontinuity, then I want you guys to be aware that this is not. That is not a removable discontinuity because the limit doesn't exist. Removable discontinuities have a limit that actually exists, but non-removable discontinuities do not. So there are two types of discontinuities. There's removable, non-removable. Removables, the limit exists. Non-removables, the limit does not. Another way that you can have a non-removable discontinuity is with an asymptote. The limit just doesn't exist. Okay. Another way you could have a non-removable with one I showed you earlier, those oscillation ones. Remember those? Those ones also are non-removable. So out of all those types of discontinuities, this one is the one that's removable. There's a slight variation to this one that's removable, and that's when there's actually a hole right above it, or I'm sorry, a dot above it, but still a hole, right? So those are examples of removable versus non-removable. So this is removable, and the rest are all non-removable. Okay? Yeah.
All equations like this one can be removable. Other exceptions.
All the equations?
All the like discontinuities that look like that.
Like this? Those are all removable discontinuities. And because here's what the definition of a removable discontinuity is. A removable discontinuity is one that's discontinuous, but the limit exists. And the only way that's going to happen is if there's a hole, right? With all the other ones, that wouldn't happen. So that is what a removable discontinuity is. So let's talk a little bit more official here on what's on your notes. So what is a removable discontinuity? If we can somehow change a function with a discontinuity, like x squared minus 1 over x minus 1, if we can change it by, like, maybe, say, for example, factoring and canceling, so that we get a new function that doesn't have that discontinuity, then that's called a removable discontinuity because you can remove it, right? Removable discontinuities are points for which the limit exists, but one of two things happen. Either there's just a hole there, or the limit exists and the function exists. They're not the same. In other words, there's a hole with a dot above it. Okay? Why do we care about these? Because it helps us find limits. It's a strategy where we've only learned one way to find the limit of a function when we just have an equation. It's direct substitution. But direct substitution will fail with an example like x squared minus 1 over x minus 1, right? But now we can remove it and then do direct substitution. So that's why we care about these. So how do we do this? Like I told you, there's going to be 3 algebraic tricks we're going to learn to remove discontinuities. One of them is the one that actually 4 ways. One of them we're going to learn about is factoring. That's today. Tomorrow we'll learn about 2 other strategies, rationalizing and something involving complex fractions, okay? But after I teach you all those complicated strategies, I'm going to show you a 4th strategy, and then you're going to be angry because you're going to say, why did you spend 2 days on this, and these take a long time and they're hard? Because this 4th strategy actually works for all of them, and it's extremely easy. So why do we bother even learning it? Well, they demonstrate a lot of good math concepts, so I think they're worth investing time in. But when we actually get to this 4th one, you'll be happy because it does all 3 of these, and it's really easy. Okay? Huh? I think so. There is one exception. There is one exception. It doesn't always work for ones like number 2 here, but it's very rare that it doesn't. But I've seen examples where it's called L'Hopital's rule. It actually fails sometimes here, but it's extremely rare to even see this. But it almost works on everything. It's ridiculous how awesome it is. So you'll be thankful once we get there. All right, so let's go ahead and write down example 1. Here you go. Now, I don't want you to write what I'm about ready to write. I just want you to watch, and then I'll tell you when to start writing. So we're going to go about our business here, la-di-da. We're going to just try direct substitution. You always try direct substitution first. Always. You don't want to waste your time and do a whole bunch of hard math when you can just plug the number in. But I can see right away that if I plug in -1 here, I get 1. If I plug in -1 here, I get -1, and that makes 0, which is not supposed to be on the bottom, right? So direct substitution fails. Direct substitution fails. So we need a strategy for this. And the strategy we're learning today is factoring. So now in my last block, I wrote something wrong. So I don't want you guys to write this. I want you guys to watch. I'm going to write something wrong on purpose, and then I'm going to fix it, okay? This is what I did last class, right? So just watch me for now. The strategy we're learning is we factored this. So let's factor that. What times what makes x squared?
X.
And what times what makes 4?
2.
2 and 2, or 4 and 4. Now, is 2 and 2 good?
Yeah. No.
It won't work. Here's why. Even though 2 times 2 makes 4, when you FOIL this out, you're going to get 2x and 2x, and that needs to make the middle, which it doesn't, right? So we would try a different pair, right? So let's
1.
Yeah, let's do 4 and 1.
Smart.
Use whatever strategy you're comfortable with. A lot of us here at Lancaster use the box method to factor. You're welcome to use it. But hopefully they're easy enough to where you don't have to do all that hard work. But there it is. Now let's do the bottom. Now this is not a box method. This is just a GCF problem. What's their greatest common factor? X. So I'm going to take an x out. X plus 1 is what's left on the inside. Now this is where I'm going to stop and say, I wrote something wrong. And here's what I wrote. They would probably ding you for this on a free response, okay? I just said the limit of this function as x approaches -1 is equal to this. And that's not true. Now, let me cover up. If I got rid of this, is that true? Yeah. But the limit of this function is just going to be a number. So you can't say the limit of this is that. That's not true. So what you have to do is you need to write the word limit here. This is true. The limit of this is equal to the limit of this because they're the same thing. It's just one's factored. So now I'm going to let you guys write it. So go ahead and copy that down. So step 1 is to factor, okay? But don't forget to write the word limit. Very often people forget to, I forget to write the word limit there because we just want to get the problem over with. So we write one factor. I know what I'm going to do. I'm going to get it at the end anyway. But if you write that step wrong, they would hit you for that. Yeah. That's weird. I wouldn't do it, but I see what you're saying. Makes sense, but I don't know if they would take it. It's not normal math writing. But it's an interesting strategy. It might work. Yeah? Okay, now, what do you think I'm going to do next?
Cancel out the x plus 1.
We're going to cancel out x plus 1, right? So what am I going to write here?
X plus all the limit.
Yeah, don't forget you're going to write the limit. And now what am I going to write?
X plus 1.
Good. Now these are equal, right? There's no reason these aren't. This is just a property of fractions. If you've got something on the top and bottom, you can cross it off. So these are equal to each other, right? But here's what's cool. When I plugged in -1, it made the bottom 0. But by crossing that off, that's the piece that was causing this to equal 0 on the bottom. Now it's not there. I've removed the discontinuity. So now, since I've removed the discontinuity, there is no discontinuity at x equals -1. And if there's no discontinuity, what strategy can we use to find the limit? Direct substitution. So now we're going to plug in. And I want you guys to notice something now that I'm doing direct substitution. What is not there now? The limit, because now I've actually taken the limit. So the limit of this is, in fact, equal to that because I took the limit. All right? So let's simplify it. -3 over yeah, it is -3. Final answer. So this one actually has a limit, even though it had a discontinuity. So we would expect, if we graphed this original function, we would expect to see a hole there. Okay? Not an asymptote, not a jump. We would expect to see just a hole because the limit actually exists even though the function does not. Okay? So, once again, what are our steps? Step 1, factor. Step 2, cancel. Step 3, direct substitution. And I want you guys to pay very careful attention to how I wrote it. Limit, 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 no limit after you do direct substitution. That seems to be an issue, so then I have to find people do that with integrals too. They keep writing the integral symbol even after they found the integral. You gotta watch out for stuff like that. They'll ding you for it. All right, let's go ahead and write down number 2, please. No. Let me finish my lesson. All right. So, before we begin number 2, I want to ask you guys a question. You don't need to write this, just watch. What's 5 minus 3?
2.
Good.
It took too long.
Too long. You funny dog, you. All right. What's 3 minus 5?
-2.
So what if I divided these? What would I get?
-1.
-1. So what would I get if I divided these? -1, right? So when you divide two numbers that are being subtracted by the same two numbers being subtracted just in reverse order, you get -1, right? All right. So why am I telling you that? So we could think of these as canceling out, right? So long as we make it a negative, right? Is that true for plus?
No.
That's still 1, right? So we don't put a negative if it's plus, but with negatives, yeah, you need to do that, okay? So at this point, if that's news to you and you're like, oh, I better write that down, then what I would write is something like this. And then I would write this as well, just so I don't accidentally assume that that's going to be -1 also, because it won't. Okay, so if you feel like you might make that mistake later, you might want to write that down. But let's go ahead and do this one. So first of all, can I do direct substitution? You always check that first. No, because if I plug in and I get 25 minus 25 on the bottom, which is 0. So we move on to strategy number 1 here, which is factor. So what am I going to write?
The limit.
Good, don't forget your limit. Now the top is 5 minus x, right? The bottom, that's a difference of squares. Can I take the square root of that and get a nice answer? That would be x, right?
Yeah.
Can I take the square root of that?
Yeah.
So if you could take the square root of each piece and it's a minus sign, it's got to be a minus sign, remember, then it's that and that. One's plus, one's minus. Okay? Now, can I cancel something?
Yes.
I can if I
Make it negative.
put a negative, because 5 minus x is kind of the same thing as x minus 5. They're just going to make a negative when you cancel them, right? So boom, and boom, and boom. All right? So now what am I going to write?
The limit.
1 over the limit as x equals to 5.
What's on the top? -1. Don't forget to put that. A lot of times when students see this note I crossed off the top, they think, oh, it's just x plus 5 now. It's 1 over x plus 5, right? So, and now, can I do direct substitution now? I can. It won't give me 0 anymore. So now I could just do direct substitution, and that gives me -1/10. There you go. So the strategy is factor, cancel, plug. But just be careful where you're writing your limit and where you're not writing it, okay? That is a removable discontinuity. All right. You guys get to practice a little bit. There you go. Maya, what'd you do first?
I factored it.
What'd you get?
I got negative x. I got negative x minus 2 over negative x minus 1 times not plus 5. I don't know if I said that right, but yeah.
I like your first step, but I'm gonna change it a little bit. When you factor, you get -2 minus 3 on the bottom.
Yeah. That's what I meant. I got it wrong.
Okay. Okay. Nate, what do we do next?
You cancel the x minus 2 the other one.
That's right. And Sam, what do we do next? Huh? Where's Sam? There he is. Oh, okay, good. Now what? Okay. Let's do some. Is Serena here? Yes. Okay, go ahead. That's right. Direct substitution. So if we plug in the 2, Dario, what do we end up getting as a final answer? Okay. I've never even seen questions like this on an FRQ, just so you guys know. But the thing about the limits is good to talk about, like writing. I have seen limit questions, so you want to know to do that. But honestly, if you're just doing a multiple choice, I would say just show your work like this. Just blur it all together and just write your final answer. Matter of fact, this might even hold up on an FRQ because you're not really writing anything that's incorrect. You just get rid of that, replace it with something equivalent to it. I don't see anything wrong with it. Yeah. It's going to be 1 because when you plug in a 2, you get -1, but there's that negative in the front which cancels it. Aaron, what'd you do first on the number 2? Yeah. What did you factor?
I factored.
All right. How about Max? What do we do next? Good. A lot of students in my last class thought that was a difference of squares, but it's not. It's a GCF. It's not a difference of squares because that x is not a perfect square, right?
Isn't it just the same thing as you had earlier?
I don't know. Is it?
But it was negative. The first time
Oh yeah. Yeah, that's pretty similar. That's pretty similar. Jennifer, what's next? You're fired.
Oh wait, I'm sorry, I didn't notice. You crossed out x minus 1.
Good. And then you do direct substitution, right? So what's our final answer, Jen? Beautiful. All right. Next one. Jacob. What do we do? Yep, that's difference of squares factoring. X minus 2, x plus 2. And next, I'm going to go to Nikaya. What's next? Bueno. What is next, Roxanne?
Are we on number 3?
Yeah.
Just write it as 1 over x plus 2 and then substitute the x with 2. So
That's right.
So we get
1/4. There you go.
Is the number 1 supposed to be negative?
No, because when you plug this in, you get -1, right? But there's a negative here as well. All right, so that's that. Next one. Here we go. Ready? Use the graph below to determine which discontinuities are removable and which discontinuities are non-removable. So let's review. Removable discontinuities. Does the limit exist?
Yes.
Yes, right? We've been doing it for the past, 40 minutes. So the limit exists, but are they continuous? No, they're discontinuities, right? So what does a discontinuity that's removable look like on a graph?
A hole.
A hole. So here's one, and here's one. Those are the removable discontinuities. So let's write that. Removable discontinuities are at x equals -3 and x equals 2 because they are holes, right? Non-removable. Yeah, good. So there are non-removables are anywhere where the line's broken, but it's not a hole. So x equals 0 is one, right?
And x equals 6.
That's a jump. Jump discontinuities are non-removable. Where else?
6.
6. We had a little argument last class about whether that was 6 or 5.5. I'll go with 6.
Oh shoot.
I think 6 is a good, because I mean, the student brought up the point that this is about the same distance as this. They just
Well, I
put the
was gonna
6
say
in a
that
weird
everybody
spot.
else has their own line, but 6 doesn't.
Yeah. So, what kind of discontinuity is that?
Yeah, so
An asymptote. And once again, those are non-removable.
That's 5 3/4.
So non-removable discontinuity, the limit just doesn't exist. Okay, you couldn't find the limit. There's no little algebra trick you could do to get an answer. They just don't have an answer. Okay, so that's what they look like on a graph. Any questions?
Sure.
All right, let's do one really quick. I'm going to give you like 30 seconds. Just you don't need to write anything down. I just want you to stare at it and discuss with a neighbor which ones are removable, which ones aren't. And then I'm going to call on you, share them out, just about 30 seconds, okay?
I only see one.
All right, so Manny, where's the removable discontinuities at?
It's 2. Like, well, it's at, like, like 2 and then 1. Like,
The y, yeah, we only need the x value, but yeah. So we'll say x equals 2 is the removable.
I was gonna say, and it's like that because the function, like, limit, like, it exists, but, like, we don't know the other part.
That's right. I like that. I appreciate the whole answer there. So he said x equals 2 is a removable discontinuity because the limit exists, but the function does not. That's if you were ever asked to explain that in an AP test. I haven't seen them ask that, but you could. Just saying it's removable because the whole is not good enough. You can't do that. You say it's removable because the limit exists, but the function does not. That's why it's removable. So that's a good answer. I appreciate it. All right, David, where are the non-removables?
X equals -2.
Uh-huh.
X equals 4.
Cool.
Wait.
Yeah?
Isn't X equals 0 also one?
Yes, it is. That one's easy to miss. You guys see why x equals 0 is 1?
Asymptote.
Because it's a vertical asymptote. Okay? So, now, you guys are going to be angry at me, but I have to do it. We didn't finish our lesson on 3.6, so I'm going to go back to that. So get out your 3.6 notes. We're going to finish that lesson, okay? So get out your 3.6 notes. We're done with this lesson.
I was confused on one of the
Which one?
number 2.
Oh, yeah, that one, instead of plugging in a number, you plug in a letter, and then use the quadratic formula to find it. Or factoring would have worked too, I think. Did you get that? Did you end up getting that one, Brandon?
Yeah.
Okay. All right, here we go. So, write the following expression as a piecewise function. Now, we did this before, right? You take the inside, you find where it's less than 0, right? Where it's negative, in other words. And for the part that's negative, you change the sign. For the part that's not, you leave it the same, right? Okay, when you're dealing with quadratics or other types of polynomials, it gets a little bit more complicated. Just a tad. Let's go ahead and take a look at it. Ready? So, we have x squared plus 4x plus 3. Okay, so I want to find, I'm going to say equals 0. The whole less than thing isn't going to serve us very well. Well, it was, but I said don't do number 7. Good. It was actually on the assignment, like right after the name, it said don't do 7. That's because you're awesome. It's all right. It's okay to be awesome. Maybe. She's either awesome or stupid, one of the two. All right, here we go. Now, I'm not going to put less than because the quadratic kind of messes that whole thing up. So we're gonna ignore that for now. We're just going to say, where does it equal 0? Because if I know where it equals 0, then I start to get an idea of where maybe the signs might be changing. Okay, because 0 is where things go from positive to negative, right? So we're going to find where the signs change. Okay, here we go. So I'm going to set it equal to 0. And we're going to factor, right? You set each piece equal to 0, and you solve. So there are 2 places where this function equals 0, which is -3 and -1. So therefore, at both of those points, those are possibly both places where the function might be switching from negative to positive, right? And at those points, that's going to tell us, okay, where does the function change its sign? So where do I need to change the signs, right? All right, the way we're going to know this is with something that's called a number line test. We do it quite a lot in here, actually. We'll do it in chapter 4, I think, or maybe 5 a lot. So, but for today, we'll get a nice little intro into it. So what we're going to do is we're going to make a number line. We're going to put the smaller number on the left, bigger number on the right. And what we're going to do is we're going to test numbers in each of these regions to find out what's the sign. Now, we already know it equals 0 here and here, right? I want to know, is it positive or negative here? Is it positive or negative in between here? And is it positive or negative over here? So I like to use the factored one. You could use the original one. Was it 3 and 1, you guys?
Yeah.
Okay. So there's my function. So I'm going to use the factored one. I think it's easier. So can you guys pick a number from this area?
Negative 5.
Negative 5 works. So let's do negative 5 plus 3 and negative 5 plus 1. I'm writing it really tiny, so I'll just say what it says is negative 5, right? That's what we plugged in. You guys might want to do that. You don't usually need to write it, but for notes, it's nice to see it. All right. So what's negative 5 plus 3?
Negative 2.
What's negative 5 plus 1?
Negative 4.
What's negative 2 times negative 4? It's 8. Is that positive or negative? So therefore, for numbers that are to the left of 3, for numbers that are less than negative 3, does the absolute value change its signs? No. Why not? Because for any number I pick that's less than 3, my answer comes out positive. And when your answer comes out positive, you do not need to change the sign. So no change. Okay? I understand the x is negative, right? But that's what we're plugging in. It's the outcome that we're taking the absolute value of, and the outcome is positive. All right, let's do this one. What number is there between negative 3 and negative 1? So let's plug in negative 2. So negative 2 plus 3, negative 2 plus 1. What's negative 2 plus 3?
1.
And what's negative 2 plus 1? Is that positive or negative? That's a negative outcome. So for all the values of x that are between negative 1 and negative 3, the outcome is negative. Will the absolute value change the outcome?
Yeah.
Yes, it will. So we will change the signs for anything between negative 3 and negative 1. Let's do the last one here. Pick a number that's greater than negative 1. You could do 1 or 0. I like 0. I think 0 is a little bit easier. That's 3 times 1. What is that? 3, which is? Positive. Therefore, change or no change?
No change.
No change. So for anything where x is what?
Greater than negative 1.
Anything x greater than negative 1, we will no change. Not change it. Yeah. So there you guys go. That's what we call a number line test, where you have a number line and you pick intervals to find out what are the signs doing. Are they positive or negative? We're going to do that actually a lot in here. And this is one place where it's useful when you're changing a piecewise function into an absolute value function into a piecewise function. So here we go. Ready? I have 3 pieces. My first piece will be anything that's less than negative 3, right? My second piece will be anything that is between negative 3 and negative 1. And my third piece will be anything that's greater than negative 1. And remember, we have to put equal signs on these numbers, so let's just go ahead and put it in the middle. Now, what did we say would happen when x was less than negative 3? Change or no change?
No change.
No change. So my function's going to stay the same. What was my function? It's just going to stay the same. What did we say would happen when it was between negative 3 and negative 1? It would change. So this would be negative x squared minus 4x minus 3. I just changed all the signs. And what about the last one?
No change.
No change. there's your piecewise function, so you could do some calculus. You guys want to see an interesting geometry thing here? Good.
Isn't the symmetry like not functional?
You don't need to write this. I'm sorry, what?
Isn't the symmetry not functional? Line chart?
No, it's a function.
It is.
It is. So let's graph. I'm going to graph this. You don't have to do this, but I'm going to graph this. This is what kind of a shape is this, you guys? It's a parabola, and it touches the x-axis at -1 and -3. So it's going to look something like this, right? Now, where are the y values negative on this graph?
When x is between -3 and -1.
Right there, right? But when you take the absolute value of this thing, what happens to all those negative y values? So guess what the graph would look like if you took the absolute, I don't like that. Guess what the graph would look like if you took the absolute value of it? This would look the same, this would look the same, but everything down here would get flipped up like that. Kind of weird, huh?
It's like a W, a win.
That's right. All right, so you guys go. I'm going to give you one.
Give me last one.
Make me proud.
That's the same.
Here you go. Do you want to look at that homework problem?
Yes.
It kind of got answered with this.
Did not.
No, I